So we're looking at op amps today then. Now there's quite a lot in this video, so if you want to jump to any section, look at the timeline on the bottom of this video, or in the description I've put a timeline in there. You can jump to any part you like. But in summary, we're going to be looking at the primary role of op amps. We're going to be looking at the non-inverting amplifier, the inverting amplifier. We will be looking at the summing amplifier, things like slew rates and the offset voltage, which catches people out. And we'll look at some various power options. So this is all about op amps. So let's take a look. So operational amplifiers then, or more commonly known as op amps. Here's a few examples of popular op amps. These are all through-hole versions, but they come in all kinds of form factors. Some of these are part of the same family. For example, the LM358 and 2904 are part of the same family as shown on the datasheet there. Now the symbol for an op amp looks like that. Don't get confused as this being your supply. These two pins here, this plus and this minus, well, this is your non-inverting input, it's called, and this one down here is called the inverting input. And we're going to go through exactly what that is throughout this video. Over this side is where the output is normally shown, and your power is actually shown here. So the supply voltage to your op amp can be shown like that. Now, it's not always shown on schematics. Quite often, these are just omitted because it's a given that it must have power. Now you can see here I'm showing a positive voltage and a negative voltage. So yes, this is dual powered. You need a dual power supply for this, but don't worry because there are op amps out there that allow a single supply. So this would be a ground. Also, near the end of this video, I'm going to give you a whole load of options of how to deal with this dual supply to make it nice and easy for you. So just bearing in mind, you've got this non-inverting input, inverting input, your supply and the output. This is a typical pinout of an op amp. So this one's a dual op amp. You can see one here and one here. You've got output one is here from this op amp, inverting input there, non-inverting input there. This is a second op amp built in. So inverting there, non-inverting there, and that's its output. And your supply goes here and here. So this is a dual op amp, and they also come in single, dual and quad options. And just to have a quick look, here's an example internal workings of an op amp. It's built from transistors, resistors and capacitors. Here you can see the non-inverting input stage in this example, the inverting input stage, and here's your output stage over here. This particular op amp has got these special pins, offset null, for both of your inputs. They're not that common, and we will touch on this later, but for the time being you can ignore it. So the most basic configuration of an op amp would be this open loop arrangement. So by open loop, I mean the output is not looped back to either of these, which we're going to look at more thoroughly later. In this arrangement, then, when your non-inverting input is higher than your inverting, then your output will go high. When the non-inverting is lower than the inverting, then the output will go low. So in this configuration, it's really a comparator, and you would be much better off using a dedicated comparator chip for that purpose, like this one, the LM339N. This has got 4 internal comparators, and the output will be a much faster, much cleaner transition from high to low and low to high than an op amp will give you. So now let's jump in and take a look at an op amp with an example feedback loop. In this example, we take the output and we're feeding it into the inverting input. Our input signal will come here. This is the non-inverting input, and this would be our output. So at this stage, we ought to look at the golden rules of op amps. These are the ideal rules, if you like, but we're going to compare with the in reality rules. So number one, no current flows in or out of the inputs. In reality, a very small current does, but the inputs are very high impedance, and for all intents and purposes you can ignore. The output can drive any current. Well, actually no, they can't drive any current, but the output impedance is very low, particularly in comparison to the input impedance, which is exceptionally high, but the current is limited. Some op amps can drive much higher currents than others, of course. Number three, the op amp does whatever it can to make the input voltages equal. This is the key part, and yes, that is true. but you do have to take into consideration some constraints. So first up, these two, slew and offset voltages. So here's some example slew rates, and these are the example op amps I gave at the beginning. So when you're driving the output transitioning from high to low or low to high, then this TL082 can ramp it up or down at a rate of 20 volts per microsecond. And these ones are 0.5 volts per microsecond. So it looks a bit like this then. In an ideal world, if you were transitioning across a range of say 5 volts from a low to high state, ideally you want it to switch instantly from that low to high. But in reality, the op amp can't do that. The slew rate dictates that it's going to transition over a period. So at 0.5 volts per microsecond, to transition across 5 volts, that's going to take you 10 microseconds. Okay, so you just need to bear that in mind. And the next one to consider then is this offset voltage. So here are some ratings from the data sheets of these op amps, and you can see it ranges from plus minus 1 millivolt up to plus minus 5 millivolts. But what does that mean? What it means is these two inputs, your non-inverting and your inverting input, they're very, very sensitive to small change. And because these transistors are not perfectly matched, if you bought a pack of transistors exactly the same model, all in the same pack, same date code and everything, they won't be perfectly matched and they will not perform exactly the same as each other. So when you've got a pair like these two here, they're not going to behave exactly as you desire. There will be a slight offset between this one and this one. So this is telling you that could be up to 1 millivolt difference in the performance of these, up to 3 millivolts difference, and up to 5 millivolts difference. That might be this one's higher than this one, or this one's higher than this one, whatever. And this particular IC, well, this gives you 2 pins that you can compensate for that. You would just add a particular resistor value, which you'll have to work out yourself, and tie that to ground. But I'll tell you what, for all of the op amp projects I've ever done, I've never had to worry about that. And in fact, I don't think I've got a single op amp IC that has those pins on it. So that's slew rate and offset voltage then. Now, unless your project is particularly high precision, then for most instances you can ignore those. The big one to bear in mind is this one, rail limit. So let's take a quick look at that. So if you was outputting a sine wave on your op amp and this was your positive rail up here and this is your negative rail down here, you would expect to be able to drive this sine wave up to here and down to here. But unfortunately, op amps, or most op amps, have a limit, and there'll be a boundary that you cannot exceed. If you get to this point here, then you would start to clip the top of the sine wave, and if you exceed down here, you would start to clip the bottom of the sine wave. And we'll take a look at this later on the scope, and I'll do some demonstrations on it. Now, the scale of these rail limits will be given in your data sheet. Here's an example of the LM358. It's called the voltage output swing from rail, and there are the ratings there. Now, if at this stage you're not really following this, don't worry, it will all drop into place later on as we go through the examples. Also, there are op amps on the market which are called rail-to-rail op amps, and as the title suggests, you can indeed reach the positive and negative rail, or very close to them. So that's rail limits then. So the final rule here is the output has infinite gain. Well, it can't have infinite gain. It's better to say that output responds with a massive amplification factor relative to the input signal difference, and that'll become clear as we go through this video. So let's go back to where we started with this circuit then, and remember the op amp does whatever it can to make these two inputs the same. But let's just have a look at that concept in a slightly different way. Here we got a Boris Tug of War going on, and the op amp here you can see is keeping an eye on it. So you can think of this side as the non-inverting Borises, and this side as the inverting Borises, and our output is up here, of course. Now, our op amp is keeping an eye on this point here. If it drifts one way or the other, it will adjust its output, and it's keeping a very close eye on that. The smallest amount of change it will respond to. So it will detect that these two Borises have got one over on this one, and therefore it will output another one for us. But without the feedback loop, that's no good. So we need to add the feedback loop so he gets added on there. And now the op amp is happy. This is now balanced. So this op amp then is constantly compensating its output to ensure that this side matches this side and that this remains in the center. So it keeps the two balanced. So with that in mind then, let's go back to our circuit. So in this arrangement, whatever we put on this input here, this output will do whatever it takes to make this one the same. So this output is basically going to equal this input. And this is known as the voltage follower. Well, you might think, what's the point of that? Well, you've got to remember that this input has a very high impedance and this has a quite low impedance. So if you are concerned about loading down your inputting device, then this kind of acts like a buffer. You've got a high impedance input here, but then you've got a low impedance output here to drive the next stage. For example, in this thermistor circuit, here's a thermistor and here's another resistor. This acts as a voltage divider. The resistance of this changes with the temperature it's exposed to, and therefore the voltage at this point will adjust in relation to the temperature exposed to. But if you put a load on this, then this voltage divider all goes out the window. So what you can do is connect it into your voltage follower in this arrangement. This won't have any impact on this, or completely negligible anyway, and your output will be quite adequate to drive another device like an analog to digital converter, for example. Now you can adapt this voltage follower arrangement to produce some quite nifty circuits. Here's an example using a diode. A tip for diodes, in case you didn't know, this black line here, that represents the same as this bar here on the diode symbol. So that direction of current flow is that direction. This direction will be blocked, of course. But diodes have a volt drop. If you're using a Schottky, it'd be much lower, but a typical diode is something in the region of 0.6 to 0.7 volts, and it can be really frustrating in some of your circuits. So if, for example, we put 5.4 volts in at this end, we might get, say, 4.7 volts out at that end. And we can use the op amp to sort this out for us. If we place the diode here, then when we put our 5.4 volts in the non-inverting input, the op amp can see this doesn't match. So it will ramp up the output and compensate for it, and will reach a voltage of 6.1 volts, and therefore bringing this back down to 5.4 so it matches. Now we've got a perfect diode. The diode will still block current trying to flow in this direction as it normally would, but the voltage we get in here now matches the input because the op amp is compensating for this drop. Now let's look at another arrangement of the voltage follower circuit, and this one's going to be a simple current regulator circuit, and it looks like this. Now as you can see, you can hang a transistor off of the output of your op amp, and the op amp can control this transistor because we're connecting it into the base. Whatever current flows from the base to the emitter is amplified through this route. So if we put our load here, whatever it is, and our supply voltage up here, the current will flow from the supply through the load, through this transistor, through this resistor to ground. Now this resistor needs to be quite low, sort of 1 to 10 ohms or something. And the S in this instance stands for either shunt resistor, or you could say sense resistor, because the op amp is sensing this point here. So if at our non-inverting input we put a 1 volt feed, then the op amp's going to do whatever it takes to make sure this is 1 volt here at this point. That's because this 1 volt is connected into the non-inverting input. Remember, the op amp will do whatever it takes to make this match this. So it will drive its output to drive this transistor to ensure that we have 1 volt here. Now, if this shunt resistor is, say, 1 ohm, and we've got 1 volt across 1 ohm, then Ohm's law tells us that's going to be 1 amp flowing through this point. And if we've got 1 amp flowing through here, we will have 1 amp, or near enough, 1 amp flowing through this route here. Remember, no current can flow into the inputs of the op amp, so this is its only route. Now you will have some current flowing from the base to emitter because I've used a BJT transistor, but you could use a MOSFET and it would behave much better. And if, say, for example, you change that to a 10 ohm resistor, well, you'd get 100 milliamps here. 1 volt through 10 ohms, that's 100 milliamps. And therefore, your load would be driven at 100 milliamps, regardless of what this load is, because the op amp will adjust accordingly. And now if you varied the voltage here, let's say to 0.1 volts, now you've got 10 milliamps, 0.1 volts across 10 ohms, that's 10 milliamps. You've got 10 milliamps going through your load. Now, rather than having a fixed voltage over here governing the current, if we replace that with a potentiometer, now we have a variable voltage here. If we connect this to our supply rail and this to ground, then as we adjust this potentiometer, the voltage on our non-inverting input will vary. and that will control the current going through the circuit. So we've now got a variable current regulator. Brilliant. Right, it's going to get a bit more interesting now. We're going to take a look at the non-inverting amplifier, and it looks like this. We take our signal source and we feed it into the non-inverting input. And there's a tip for you. If your source is going into the non-inverting input, then it's a non-inverting amplifier. If it's going into the inverting input, then it's an inverting amplifier. And we'll see exactly what that means in a second. So in this arrangement, you can see that we still have the feedback loop from our output to our inverting input, but we have this voltage divider on its route to get there. So if you're unfamiliar with voltage dividers, I did do a video on that, and I'll leave a link in the description below. But basically, the voltage at this point here is going to be whatever this output voltage is times this divider. So it'd be this resistor divided by the total resistance of these two added together. So if we had, for example, these were both 10k and we had a 1 volt output here, then this would be 1, in other words, 1 volt at the output, times 10k, in other words, R2 value, which is 10k, over 10k plus 10k, which is these two added together. So that would give us half a volt. Now let's assume that this 1 volt is actually fed at the input then. Remember that the op-amp will do whatever it takes to make this input match this one. So it wants this also to be 1 volt. So in order for this to be 1 volt, then the output will have to be 2 volts. In other words, 2 times a half basically would give us the 1 volt. So that is a gain of 2. And the simple formula for calculating the gain of a non-inverting amplifier is that the gain is 1 plus R1 over R2. Nice and simple. So in this example, we had 1 volt here, 1 volt here. We had to output 2 volts, so we had a gain of 2. If we change this resistor to be 100k, and let's say we had half a volt coming in here now, then the output will have to be 5.5 volts, or 11 times your 0.5 volts. And if you change this to 1k, then you have a gain of 101. So if you had 10 millivolts up here, then your output would have to be 1.01 volts, 101 times your 10 millivolts to give you 10 millivolts down here. And once again, you could replace this arrangement with a potentiometer, and we could make the gain completely adjustable. As you rotate your potentiometer this way, this little resistance, this resistance on this side of the potentiometer will reduce, and effectively R2 will increase, meaning that your gain will go down. If you turn it the other way, this will reduce, this will increase, means your gain will go up. Right, so let's build this up on the bench then, and then we'll have a look at its output on the scope. Okay, there it is, all assembled. I'm using this, a TL072P op-amp. It just happens to be one I had laying around. And I'm powering the board from a positive and negative 5 volts. This is coming from my bench power supply. So my positive 5 volts I've got wired into this rail here, and negative 5 volts I've got on this rail here, and then my ground, which obviously the center point between these two, is connected on the blue rail, which is here and here. Okay, and that goes into my op-amp. So my positive supply is going there, and the negative supply into this leg. Then this yellow cable, you can see, that's coming from my signal generator, and that's going into the non-inverting input. So this is my signal generator here, okay? What's next? This blue link here. So that blue link is coming across to the center leg of the potentiometer. So that pin there is the inverting input. So the inverting input there to the center pin of the potentiometer. Then this yellow leg is actually from the output, and the output's going to one side of the potentiometer, which is the output, across on that yellow leg into here. And the other leg of the pot obviously then has to go to ground. So that is that link there. All right. Let's now connect up my scope. So I'm going to use my yellow trace, which is this one, that's yellow, and we'll connect that into the input so we can see what's coming in. Connect this obviously to ground. Then the blue trace, this one, we will connect to the output so we can see what's coming out. Okay, let's connect that up. There we go. Let's have a look at it on the scope then. Right, just so you can see the rest of the setup then, there's my signal generator. It's currently set to 1 kilohertz, 1 volt peak to peak. and that's going off into the breadboard. There's my scope, obviously, and there's the 2 channels coming in, and we'll look at this closer in a second. And this is where I'm powering it from. So this is my bench power supply, really nice power supply. I like this. And I've got the 2 channels on here, so it's a 3-channel power supply. The first 2 are on, and they're both set to 5 volts. My negative supply comes here, then it goes here, across here. So that effectively, so this is 5 volts, then that would be 10 volts there. But I'm taking my ground from this center point. So if this is my ground, therefore this would be minus 5 volts. So minus 5, then ground, and I've got a little link wire there joined across, and that's my plus 5. Okay, let's go and zoom into this then. Right, there you go then. I've got both signals showing there. So channel 1, that's the input, and channel 2, that's my output, the blue trace. And as you can see at the moment, it's set to unity gain. So I've got that potentiometer cranked right round to the left. So it's almost bang on with the yellow line. Now if I turn the potentiometer up and increase the gain, you can see it's amplifying the output signal. Okay, and currently at 1 volt per division here, so you can see the kind of scale of amplification I'm getting. But if I carry on going up, you see what happens. Okay, we're going to have to, you just about see it there. Let's just change this to 2 volts per division, so we keep it in the display. So that's 2 volts, and channel 2 is now 2 volts per division. As I turn this up, you can see the top and the bottom of the sine wave on the output is getting clipped, and that's because we're reaching our upper and lower threshold limits. So if I just put on my cursors, and there we go. So this line here is my supply voltage at 5 volts, and this is my negative supply rail at minus 5 volts. As you can see, I can't reach it. It's clipping before I get there, and that's the rail limits of this particular op amp. If I reduce the amplification a bit there, and if I change the offset voltage, if I put a DC offset voltage on my input signal, so if I go offset and then I push it upwards, there you go, my input signal's gone up, the output signal's lifted up. You can see I'm cropping the top of the signal. If I take the offset down, and now I'm cropping the bottom. So yeah, you got to bear that in mind, your rail limits. Some op amps are rail to rail, as I said, and that's all great, but they'll have other limitations. You need to just check the data sheet. All right, so that's the non-inverting amplifier. Brilliant. So that's the non-inverting amplifier then. And remember, if your signal source is coming into the non-inverting input, it means it's a non-inverting amplifier. And now we'll look at the inverting amplifier, and it looks like this. Now you may have spotted there that I've flipped around the inverting and non-inverting input here. So my plus is here and negative here. And you'll see that quite often. It'll just be arranged in the most convenient and easiest way to view it. So flipping them back front, absolutely fine. And as you can see in this arrangement, my inputting signal is going to come into the inverting input. That's because it's an inverting amplifier. Now, the thing that confuses people about this arrangement is that your non-inverting input is tied to ground. Remember that nothing flows in or out of this terminal. We're just tying it to ground as a reference. So let's just label these R1 and R2. Now, remember that the op amp is keeping a very close eye on these 2 terminals and comparing them. So if this is 0 volts, then the op amp will do whatever it takes to make sure this is also 0 volts. Now, bearing in mind that nothing can flow in or out of this terminal either, then the only path that current can flow is that. Now, if you're concerned about your load pulling this signal down, you could always add another op amp here in a voltage follow arrangement, and therefore your load would go here, and your amplifier would be unaffected by it. Now, the formula for calculating the gain of an inverting amplifier is that it's minus R2 over R1. So if we had a 10k resistor here and a 100k resistor here, then your gain would be minus 10. So let's say, for example, we had 1 volt here. Then with a gain of minus 10, you would have minus 10 volts here. Well, how does that work? Well, let's run through it. So remember, this is tied to 0 volts, and therefore the op amp will do whatever it takes to make this 0 volts. So if we've got 1 volt here and 0 volts here, we've got 1 volt across this resistor. 1 volt across 10k, that's 0.1 milliamps. And remember, nothing can flow in or out of this terminal. So the only path that this current can flow is that. It will come from your input through this resistor, and then in or out of the output of the op-amp. So if you've got 0.1 milliamps here, this is the only path it can flow. You must have 0.1 milliamps here also. And 0.1 milliamps times 100k resistance, well, that's 10 volts. Now, bearing in mind the current is flowing this direction, we start off at 1, go to 0. We've got to be reducing in voltage, so that must be minus 10 volts. So what's happening is when you have 1 volt here, the op-amp has to output minus 10 volts in order for this to become 0. So that's why we say it has a gain of minus 10. Positive voltage here, negative voltage here. If you've got a negative voltage here, you get a positive out here. And 10, well, that's just the multiplication factor based on these resistors. So let's suppose your input signal looks something like this, maybe an audio signal. Then your output would look something like this. It's inverted, believe it or not, that is inverted to that. And it would be amplified, of course. And the amplification is based on these 2 resistors. So the key to this amplifier arrangement then is these 2 are 0. This is tied to ground, and the op-amp will do whatever it can through these resistors to make sure this is 0 volts. And this is known as virtual ground. You might have heard people mention virtual ground before. That's what it means. It's not actual ground, that's here. But this is driven to 0 volts through this output of the op-amp. Now, one of the big advantages of the inverting amplifier over the non-inverting one that we saw earlier is that from your inputting device, this looks like ground. So you could actually put 2 input devices here and they won't affect each other because this is going through this resistor effectively to ground and this is going through this resistor effectively to ground. This will not interfere with this. And this is called a summing amplifier. And the op-amp will continue to do whatever it takes to make sure this point here remains at 0 volts because that's what's on its non-inverting input. And it will do that regardless of how many of these inputs we put. We could put a 3rd or a 4th one here and it would still continue to operate the same. Now this arrangement is actually a really handy audio mixer. You can have various audio channels coming in, combine them all together and get one audio source going back out again. And actually we're going to do exactly that in a short while. But before we do that, let's have a look at the calculations for this amplifier then. So first of all, the gain for input 1 is minus R2 over R1.1. It's the same as the previous inverting amplifier arrangement, but of course you're talking about R2 and R1.1, this resistor here. And the gain for this one, input 2, would be R2 here over R1.2 over this resistor. Now the total output gain is a collective of the voltages coming in here and these resistors, and it's calculated like this. So your output voltage is minus R2, this resistor here, multiplied by the V in 1, this voltage coming in here, whatever it is, over its resistor, R1.1, plus V in 2, this voltage coming in here, whatever it is, over its resistor 1.2, and you can keep going on if you've got more and more inputs. And that would tell you the voltage out that you can expect for that moment in time, whatever these voltages are. And remember, of course, it's inverted, hence the minus sign there. Now, if that's a problem to you, then just add another inverting amplifier here, probably unity gain, and it'll put it back to its normal orientation. So let's go to the bench, build this up, and we'll take a look at this one on the scope. And there you go, that's the summing amplifier all assembled there. I'm using this TL072P op-amp. You could use pretty much any op-amp for this. It just happens to be one I had to hand. And I'm using 10k resistors for everything here, so it's all unity gain. So first of all, we have these 2 resistors over here coming from our inputs. Well, we haven't wired them up yet, but our inputs will go through this resistor and this resistor, and that goes to our inverting input. That's these 2 here. Our inverting input is there. Then you need this feedback resistor, R2. Again, that's 10k. So that goes from the output again to your inverting input, and that's this resistor here. And then this leg, your non-inverting input, is tied to ground. So that's this leg here. So I'm running this from my programmable power supply. I'm using 2 channels and tying them together. So I get a +5 rail and a -5 rail and a ground as well. And that's my supply voltage going in here. So that's the +5 going in here. And this is the -5 going there. All right. So let's have a look at it working then. So what I've done now is I've plugged in my signal generator. I've got channel 1 going to the first input on that summing amplifier. That's through the 10k resistor. And I've got channel 2 going to the second 10k resistor into that inverting input. And then I've connected up 3 scope probes, as you can see. So the yellow trace will be the channel 1 input, so we can see what's coming in. The blue trace will be the channel 2 input, so you can see what's coming in on there. And the purple or pink trace, whatever it is, that's the output of the summing amplifier. And we'll have a look at the scope over here now, and we'll zoom in a bit and see exactly what we're getting. Right, there you go. That's channel 1 from my signal generator, and that's going into the first input of that summing amplifier. Let's turn that one off, turn the blue trace on. Yeah, I'm triggering on channel 1s, that's why that's all over the place, but let's just stop that. There you go. That's the waveform I've got coming in from my channel 2 output from my signal generator. That's called a multi-tone signal. Okay, and then let's look at the outputs. Let's get that running again. There's our output. So that should be the 2 signals added together. Just stop that. That should be the sine wave and that multi-tone added together. Now, if I bring it all on to display at the same time, run it again and stop. There you go. You can see the purple trace is this kind of blue signal superimposed on top of that sine wave. Look, it's going up and down with it. All right, so brilliant. It is adding it together. So what I've done now is I've replaced that signal generator with 2 audio devices. I've got an old Samsung tablet and an old Samsung phone here. And then that allowed me to inject audio into our summing amplifier. So I've taken the right-hand channel from this and this to go into the 2 inputs. And of course I've had to common up the ground between here, here, and the ground on the breadboard, of course. So it's still powered by the ±5 volts. And I've got over here a little cheap amplifier and a little speaker on it out of a television years ago. So that quality is not going to be great, but it'll demonstrate that you can use this for combining audio. So first of all, if I do this one then, let's just move my mic. And if I wire my supply like that, so pin 8 is to my 9 volts. Okay, and then stop that. Of course, I've got to tie this. And then we'll start the second one. So that is a 555 chip in a nutshell. You've got your voltage divider here. They go into these 2 comparators and the 2 highs to prevent this flip-flop from, and in addition to that, reset driver. So now this is a PNP and can source sufficient current. You've got a reset pin which goes via this track. There, brilliant. You can mix audio together. So that's the summing amplifier then. Now, as with all the circuits I've shown in this video, I've only shown you the most basic arrangement. There are improvements you could do and probably should do with all of these. And I will do more follow-up videos in the future, probably on this one first actually, because I want to build one of these for my office. I've got a Amazon Alexa and I've got my PC connected to the same speakers, and it'd be quite handy to have yet another channel to go to my speakers as well when I need it. But I want to enhance this a bit and make it a bit more robust, you know, with some blocking capacitors, maybe some further stages, and I might do a little project on that and a further video. But for now, let's deal with this elephant in the room then, this dual power supply business, and I'm going to give you a number of options. So first up, using a bench power supply and how you would wire that to give you a positive and negative voltage. Similarly, if you're using batteries, how you get positive and negative voltage out of that. Another option is to use DC biasing to kind of kid your op amp that you've got a positive and negative rail, but you haven't actually. You could use voltage converters, and I'll give you an example of that. And we'll touch again on single supply and rail-to-rail op amps. And then this elephant in the room, well, he becomes insignificant. So to start with then, let's look at this one, bench power supplies. Now this is the power supply that I use, and it's what I've been using throughout this video. If you've got a power supply of your own and it's got 2 or more outputs, then you can utilize it. So first of all, you need to wire up like this. You take your first supply and take the negative output from that. You then need to link the positive to the negative of the next one, and then take the positive supply of that, and that would become your positive supply for your op amp, this becomes your ground, and this becomes your negative supply. So when you power up your supply, let's say you had this as 9 volts and this is 9 volts, so this channel is 9 volts and this channel is 9 volts, then ordinarily this would be ground or 0, and that would be 9 volts. This would be ground, and that would be 9 volts. Or if you wired them together like this, then you could say, well, that's ground, that's 9 volts, this is still 9 volts, and then that would be 18 volts. But as we're using this as our ground over here, then you're referencing from that point. So from here to here would be minus 9 volts, and then from here to here will be plus 9 volts. So you've got your dual supply. And you can do exactly the same thing with batteries. So here's some 9 volt batteries. You could use AA, AAAs or whatever batteries you like. But you just do the same thing. You take your positive supply from here, you link this to this one, and then you take your negative supply from there. So with these two 9 volt batteries, you'd end up with that 9 volts and minus 9 volts. And this center point here is your ground. So now let's look at this DC biasing then. So assume that you are outputting a sine wave from your op amp with a dual supply. Then your positive supply would be here. Your negative supply would be here, and your sine wave would alternate around your ground. Here's my ground here. Now remember that I said that most op amps will not allow you to reach the positive and negative rail. There'd be a threshold that you can't exceed. And as we saw in the demonstration earlier, if I expanded this sine wave through its amplification, then you will actually end up cropping the top and the bottom of that sine wave, which we don't want. Or if you put a positive DC offset for your input, for example, then you would crop the top of your sine wave. And if you did it down the bottom, you'd crop the bottom as well. Now, let's assume we didn't have a dual supply and we only had a single supply. So your ground would now be down here. You've got ground and your positive supply, and your sine wave would alternate around your ground down here. But your op amp output won't allow you to do that. You've got this boundary here. So you'll end up with a sine wave output like that. Horrible. So let's assume we had, in this instance, a supply of 16 volts. So each one of these is 2 volts. Our midway point here would be 8 volts. 0, 8 volts halfway, then another halfway, 16 volts. If we can offset this output by 8 volts, then we will lift it back up here, and it will sit back in within the boundaries of our op amp. And there's a really simple way to achieve that. So let's just have a look at this example of a non-inverting amplifier then. So we'll be inputting a sine wave and we'll be outputting a sine wave. It's non-inverting, so it's same orientation, but it's amplified, of course. So ideally, you would power this amplifier with a dual supply like that, positive 8 volts and minus 8 volts, and your ground would sit in the middle. So over here, your sine wave would sit in between your positive and your negative rail. But that's not always achievable, and in many instances you want to be able to use a single supply. But you're going to end up, as we just seen, with your sine wave down here, and it will get horribly clipped. So we need to lift this sine wave up by 8 volts, which we will do from the input side. So let's just move this down to make a bit of space. Now, first of all, we'll put a capacitor here to block any DC current going this way or this way. And then we'll add the good old voltage divider, 2 resistors here. We'll connect this to our supply voltage and this to ground. Now, let's suppose these were both 100k. Then at this point here, we will have 8 volts. Our AC sine wave will alternate around this 8 volt bias, which is exactly what we wanted. Now, you should also put a capacitor here. Otherwise, this 8 volt DC, you will also be amplifying through here. By putting it here, the DC element that's coming out of the output will be blocked to ground, so this voltage divider does nothing. It will just pass straight through, whereas the AC element will pass through that capacitor absolutely fine. So now our output will be raised up to 8 volts, and it'll be centralized between our upper and lower rail, this being ground and this being 16 volts in this instance. And of course, this sine wave will be an amplified version of this one based on whatever resistors we chose. Okay, so that's DC biasing. And now we'll look at this, voltage converters. I've used this chip quite often actually, the 7660. And in this circuit here, which comes straight out the data sheet, if you have a look, this is a simple negative converter. So whatever you put in here as your positive supply, you'll get a inverted version of that. So if I put 5 volts in there, I'll get minus 5 volts out there. Brilliant, does exactly what we need. And you can use this chip for all kinds of instances. This is the circuit for splitting a supply in half. So if you had a positive here and negative here, this point here would give you exactly half of that. And I guess the reverse of that is a voltage doubler circuit, which is shown there. So that's the voltage converter option then. And just bear in mind that there are single supply op amps out there. Actually, the LM358 is kind of a single supply op amp. When you look at the negative rail, so the voltage output swing from rail, negative rail, depending on what current you're drawing, typically 100 millivolts. So you can get very close to it. So rather than this horrible clipping that you're going to get down here, if you've got this as your positive voltage and this as ground, the LM358 will let you get very close to this rail. And if we change the offset on this sine wave, yeah, you can get it within the bounds of that op amp. And you'll find there's variants of most op amps. Some are high precision, some are rail to rail, and all kinds of benefits they might give you. So a variant of the 358 is this one, the LMV358, and that is a rail to rail op amp, which is specifically stated on the data sheet here, rail to rail output. And as you can see, it does let you get very close to the supply rails, 20 millivolts in that instance. So basically you can kind of ignore those boundaries and you could expand your sine wave to almost reach your positive and negative rail. So that covers rail to rail op amps, and that's the end of all of those dual supply options. There are countless others, no doubt, but at least that gives you some ideas of how to get around that big elephant in the room. And if you made it this far through the video, then well done. It's been quite a long video. It's taken a long time to produce, as you probably can imagine. So if you have enjoyed it, please make sure you subscribe and please click the like button too. Okay, catch you later.